and that it will be having a very high charge density, high polarizing power. Okay, then of course, even though they form an ionic compound, then that negative charge ion actually would be distorted, greatly by this positive 4 cation. Then as a result, you find that the compound that is formed later on would be very covalent, having a very significant covalent character. Okay, so might as well just form a covalent compound lah. Why bother want to find, form an ionic compound and yet with very strong covalent character, isn't it? Not worth it. So that's why group 14 would just prefer share direct form covalent compound rather than, use a lot of energy, produce a positive charge ion, forming an ionic compound, which showing very great covalent character. No point in doing that. Okay? That means it can achieve stability just by share electron. No need to donate electrons. Okay? So that means two reasons why group 14 do not prefer to donate 4 electrons. Number one, the ionization energy will be too high. Number two, the ion that produced after donate 4 electrons will be, small in size, high in charge density, thus having a very strong polarizing power. So that means the ionic compound that they form later on, that negative charge ion electron cloud will be greatly distorted by that small size, high charge density, positive ion. Then the ending result, the compound form by right is ionic compound, but would be having a very strong covalent character. Okay. Now, of course, you should get that the so-called ionic compound with a covalent character, meaning it doesn't show the properties of ionic compound. Instead, it shows a lot of property for covalent compound. That is what it means by having a covalent character. That means we studied last time. Ionic compound, let's say number one, having high melting boiling point. Number two, soluble in water. Number three, can conduct electricity in a molten or aqueous solution. Okay, let's say that would be the great character. So actually, let's say it's ionic compound. Suppose it has these 3 character, but we find that some of the compound is ionic, but they do not have this character. For example, ionic compound and yet they insoluble in water, which is not logic. By right, ionic compound soluble in water, but you find that some ionic compound insoluble. So of course, one of the reason is because they are actually having a little bit covalent character. Because covalent compound supposed to be insoluble in water. Okay, but of course, everything having exceptional case. Okay, so one of the reason for that exceptional case is, for example, because actually that compound having slightly, little bit characteristic of the other compound. Okay, but anyway, that means all this most of the time you just follow the statement. Yeah, that is how we take exam, isn't it? Just remember how to write the answer, because sometimes you need to read a lot for you to be able to connect everything and get a very clear picture, understand everything. Or else sometimes, of course, you just can't get it. Then for exam purpose, because we all know, get the standard answer, memorize it. Now, of course, positive for oxidation state, as I mentioned, definitely will be covalent. None will be ionic, okay? Because to form the positive 4 charge, too many, obstacles, Okay, so I find that comparatively, in fact, a positive for oxidation state is stable for the elements on top especially. Like CO compared to CO2, CO2 is more stable. So positive 4 oxidation state actually is more stable. Okay, similar SiO positive 2 compared to SiO2. You find that SiO2 actually is more stable. Okay, and well, the example here. So positive 2 oxidation state actually is more stable for elements at the bottom, especially lead, as in PbO. That means if you compare PbO and PbO2, definitely PbO is more stable. So in fact, based on the example, more or less we know. So on top, positive 4 oxidation state will be more stable. So going down the group, positive 4 oxidation state, stability decreases. And then, but going down the group, you find that positive 2 oxidation state become more stable. Okay? Okay, so let's check in detail, or should we say revision a little bit, how to form that positive 4 oxidation state. Okay, so we check now, electronic configuration in the valence shell for positive 2 oxidation state, of course, will be this one. So there, positive 2 only, isn't it? Because your S already paired up, no need to share, so only share this 2. That is how we get the positive 2. Okay. So now, when one of the S2 electron, you promote it to the empty orbital, during excited state, then of course you're going to get the positive 4 oxidation state. I mean this one, isn't it? So this is a so-called positive 4. So of course this type of promotion, that's what we said as it undergoes sp3 hybridization. Okay. So, of course, you find that the positive 4 oxidation state, of course, requires energy because you want to promote one electron from the s orbital to the p orbital because it, move up energy level. So you need energy to do that. So if the energy required to promote that electron can be covered up, is compensated by the energy released during covalent bonding, because we all know when a bond is formed, energy will be released. Definitely, it doesn't matter what type of bond. When you form a bond, because you imagine when a bond is formed, the particles settle down, less movement, some even cannot move freely already. Then of course all the extra kinetic energy especially you need to release them. Then it will settle down. So formation of bond definitely release energy. So you want to promote that one electron from the s orbital to the empty p orbital, you need energy. Once you promote, then of course it will having 4 unpaired electrons. So then it can form 4 covalent bonds, isn't it? So during the formation of that covalent bond, of course energy will be released. So if the energy released can cover the energy needed to promote, then you find that of course that element definitely would have a very stable positive 4 oxidation state. Then of course the reaction would take place, can compensate it. Okay, so then, but of course if the energy needed cannot cover by the energy release, then of course the element is not going to do that. Then of course you find that positive 4 oxidation state not taking place. Why want to promote? Need a lot of energy, and the energy not cover up later on. Okay, like you are doing business, if you do not earn anything, why want to do it? So similar with this type of chemical reaction. Okay, that, as I mentioned, if cannot cover up, then of positive oxidation state not stable might just maintain positive too. No need to promote anything. No excited state. Okay, that will be the case. But of course, this is how we write the statement. Clear? When under what condition will an element having a positive 4 having a stable positive 4 oxidation state, there, if the energy required to promote, okay, is compensated by the energy released during the formation of the covalent bond, okay, if this condition is fulfilled, then of course a stable covalency of positive 4 will form. Okay, if the energy required cannot compensated by the energy release, then of course the element is not going to be stable in positive 4. Then just might as well maintain positive 2 lah. Because positive 2 no need to promote anything, no excited state involved, just maintain ground state. Okay. So now you find that going down group 14, of course the atomic radius increases, size getting bigger. So strength of the covalent bond, of course, weak because two atoms far from each other now. Far in a sense because they are getting bigger. When big, automatic the distance from nucleus of A to nucleus of B, that distance getting further away, isn't it? Then automatic covalent bond, weak. Now, when a bond is weak, the energy that it can release, of course, also less. Isn't it? Similarly, you want to break a strong bond, you need a lot of energy. So actually similar, when a strong bond is formed, the energy release, of course, will be great. This one, So now going down group 14, size getting bigger. So the covalent bond, of course, getting weaker. So that means when the covalent bond is formed, you find that less energy will be released. As a result, of course, the positive 4 oxidation state becomes less stable because the energy required to remove electron, is high, and yet the energy released when the covalent bond is formed. Sorry, not release. That means the energy required to promote the s orbital electron to the p orbital electron is high. You need a lot of energy to do that, and yet the covalent bond that it formed later on release not a lot of energy. Then you find that the energy released and the energy needed not cover up each other. Then of course as a result the element is not going to do that. Even doing that also, that positive 4, that means that situation is not stable. So that's why going down group 14, positive 4 oxidation state becomes less stable. Okay? So that means you are making use of this type of reasoning to explain why going down group 14, positive 4 oxidation state becomes less stable. Okay, that would be the reason. In fact, the last element in 14, Pb, positive 4 oxidation state is very, very unstable. In fact, it will prefer positive 2 only. Okay, now of course if question asks why, that means why in Pb to promote, okay, I mean the one of the s2 electrons to the empty p orbital electrons, to the empty p orbital, why actually need a lot of energy to do that? The promotion, isn't it? Now of course that one is due to one of the factor, or should I say one of the conditions which we call it as the inert pair effect. Okay, so we are looking at lead. Okay, lead period 6. So the valence electron, of course, will be the 6s2 and 6p2. So if lead want to get positive 4 oxidation state, meaning one of these s2, one of the electron in this s, you need to promote it to the empty orbital of the p. Okay, so you find that to do that, a lot of energy is needed because the energy difference between 6s and 6p actually is very high. Right? So that means 6s electron is hard to be promoted to the 6p orbitals. So As a result, the two 6s electrons will remain as an inert pair. They prefer just maintain a pair in that s orbital. Okay, so meaning that two already full, so not involved in chemical bonding. So this condition is called the inert pair effect, which of course is shown by lead. So if question asks you why lead, uh, not stable in positive 4 oxidation state, well, this is how you explain. Because the 6s electron, okay, in lead experience a condition which we call an inert pair effect. Where the 6s electron is hard to be promoted to the 6p orbitals due to very high energy difference between the two levels. Right? So as a result, the 6s electrons will remain as an inert pair. Okay, they're not going to be promoted to the 6p. So they're not involved in any chemical bonding. So meaning in lead, Pb only two orbital which is half filled. The P2 only having half spin. So they can share with another two atoms only. Enough? Okay? So therefore, lead tends to form a stable compounds with positive 2 oxidation state. Okay? That means when you are comparing the positive 2, positive 4 oxidation state, we just look at that oxidation state. You don't bother about, that means we assume we are talking about sharing lah. Okay, we assume both the oxidation state is sharing of electrons. We don't really go and differentiate them by one is share, the other one is donate. We don't do that. That means you just explain in terms of assuming both of them share electrons. Share 2 only or share 4? Okay. So you find that going down group 14, positive 4 getting less stable. Positive 2 getting more stable. That's what you need to know. Okay, or of course, let's check how are you going to give reasoning. Okay, so the stability. So going down group 14, of course, strength of the covalent bond decreases. So less energy is released. So the energy release is not sufficient to compensate, okay, for the energy required for the excitation, okay, to form the positive 4 oxidation state. Now the so-called excitation, that means the formation of the excited state. That means when you want to promote one of the pair as orbitals, as electrons, you want to promote one of them to one of the NTP orbital. So to do that, of course, energy needed, isn't it? So that energy needed not compensate by the energy release because the one release is less. After all, the bond is weak, okay? Then of course, the stability of positive 4 oxidation state decreases, okay? And of course, there's an increasing tendency for group 14 elements to show a valency of positive 2. Okay, in fact, I mean the decreasing stability of that positive 4 oxidation state, of course, is shown in a standard electrode potential. In fact, we can check this too. I mean, when you look at this value, okay, you find that the answer getting more positive, more positive, more positive. Right? Now, of course, we all know when E naught is positive means which one is more stable? This is from your chapter 8. That means this one, of course, showing PB from 4 becomes 2. Then you find that if your E naught answer is positive compared to negative value, isn't it? So positive, negative, of course, one of the application of the E naught is you are able to decide which one is more stable. Of course, if you still remember the E-NOx application, I think I give you about 7 different applications. So if the answer is positive, means product is more stable. Okay, you make sure you remember that. If the value is negative, means the reactant is more stable. So from the E naught, of course, there it proves that. I mean, if you look at PB, it's a positive value. Positive value means the reaction spontaneous, Spontaneous, of course, means 4 spontaneously change to 2. So means 2 is more stable than 4. But if you look at, A, the value is negative. Negative, of course, means the reactant is more stable. Or in other words, if it is negative, means the reaction is not spontaneous. So in other words, means, germanium 4 not willing to change to germanium 2. The reaction is not spontaneous, no. You force it, then it will take place. So in other words, of course, means germanium 4 is more stable compared to germanium 2. And so that means it's not just because we are talking about the energy needed for the promotion of the s electrons to the p orbital is a lot. Not just we discuss about the energy, just talking, using statement, but the standard electrode potential actually, proof that situation. By looking at the value, actually it tells you that, this reduction process is not spontaneous. You need to force it to take place. So in other words, means germanium prefer to be in positive 4, okay, rather than in positive 2. So the conclusion, positive 4 is more stable, okay. But when you look at lead, the E naught is positive, so it means, this reduction process spontaneous. So in other words, means PB prefer in positive 2 rather than positive 4. Okay, that will be the case. There, as E naught's values become, increasing positive going down the group, of course the tendency for the 4 to get converted to 2, of course, increases. Okay, I mean the reaction becomes spontaneous. Okay, of course you find that for the first 3, okay, carbon, silicon, germanium, of course a positive 4 oxidation state, very stable. Okay, positive 2 oxidations.
老师 S 要进来。
Okay, Edson, welcome. 你是谁啊？看半个钟头过去了，你再不起来的话，你再不 join 的话，我就电话打过去的了哦。Okay, so let's continue. Okay, so let's see. Okay, carbon, silicon, germanium, of course, very stable at positive 4 oxidation state. Okay. Now, so in other words, means if they are in positive 2, then they would, should we say, in a very fast manner, they would try to change themselves to positive 4. So that means positive 2 to positive 4 increase, so mean is oxidation. So if they want themselves to undergo oxidation, then meanings they would act as a reducing agent. And so that means carbon, silicon, germanium, they have monoxide, positive oxidation state, isn't it? So most of them would act as a strong reducing agent, so that they themselves can undergo oxidation and change from 2 to 4. See that? So that means the positive 2 oxidation states compound for carbon, silicon, germanium, normally they will act as a reducing agent. Okay, I mean, for example, carbon monoxide, okay, act as a reducing agent, reduces, iron 3 to iron. So itself oxidize from positive 2 to positive 4, and from carbon monoxide to carbon dioxide. So it acts as a reducing agent. Okay. In fact, this concept is applied in the extraction of iron from iron ore, which you studied last time. So they make use of CO as the reducing agent. So for example, carbon monoxide react with iron 3 oxide, isn't it? Then you're going to get the product carbon dioxide and the iron. Okay, so this concept is applied in the extraction of iron. This is what happens, when they process bijay besi, long bond bijay besi, isn't it? This is what happens. They make use of CO. And how to get CO? Of course, you start from C lah. You burn your carbon in limited oxygen, then you get the CO. So that CO, of course, can reduce your iron 3 oxide to iron. Carbon also can reduce iron 3 oxide to iron. Of course, also can. Okay, so that in industry, carbon monoxide is a strong reducing agent and normally used in the extraction of iron from its ore. Okay, okay, now other example, let's say silicon. Silicon monoxide, silicon 2 oxide, silicon monoxide. Of course, not stable because just now we already said when the inox value is negative, or if you check this one inox value, this one, even though for I don't show silicon here, but of course if you check back silicon it's definitely negative answer. Okay, so it is negative. So if negative means not stable, isn't it? It will prefer to become 4. So silicon 2 oxide, of course, is also unstable to exist at room condition. Because this one under room condition, it is a glassy solid, isn't it? Okay, so the simple molecule is not stable at all. Okay, that means it exists only in the gaseous state at about 2000 degrees Celsius. Okay, so the stable oxide of silicon definitely is a silicon 4 oxide. This one is stable. Okay, SiO is not stable, especially in simple molecule form. Okay, germanium also forming 2 oxides in it, the monoxide and the dioxide. Now, of course, the monoxide readily converted to the dioxide. So again, 4 is more stable than 2. Because readily take place, this one. Okay. And if you check tin, now positive 4 oxidation state still slightly more stable compared to positive 2 for tin. Okay, that's why tin 2 still actually is a good reducing agent. Still can act as a reducing agent in quite some chemical reaction. Okay, but of course it's weak already. Okay, that for example, tin 2 chloride can reduce iodine to iodide. So it self-oxidized to, positive 4. Okay. So for tin, actually still positive 4. It's slightly more stable than positive 2. Okay. This one still take place. So your tin 2, okay, oxidized because the reducing agent, so it will reduce your iodine to iodide. So itself, of course, oxidized to tin 4. Okay. Now, tin 2 chloride also can reduce mercury 2 to mercury 1. Still can act as a reducing agent. Tin 2. That means it still prefer to change to tin 4. Okay. So mercury 2 to mercury 1. So tin 2 becomes tin 4. So mercury 2, even this one is positive 2, becomes mercury 1. Okay, this is mercury 1. And of course, that means this one, you just remember, this is how we write the formula for mercury 1. Hg2Cl2. We don't simplify the value, okay? Just as hydrogen peroxide lah, H2O2. Nobody is going to simplify it become H and O. That. Okay, so that'll be the case. And in fact, it still can keep on reduce the mercury 1 to mercury only. So it can act as a reducing agent. Okay, keep on. This one is a mercury 1, yeah, positive 1. This one is 0, okay, mercury only. So that means the reduction process can be on and on, just using one type of reducing agent. Or even this one, it also can change iron 3 to iron 2, also can. Isn't it? Iron 3 change to iron 2, so tin 2 becomes tin 4 reduction. Okay. Of course, it also can reduce manganese 7 to manganese 2, also can. And then, okay, manganese 7 to manganese 2. Now, balance this equation. If you look at this one, it seems like balanced already, but it's not. Because you need to know, redox, oxidation reduction, by right, is formed. I mean, the overall equation is formed when you combine the oxidation half and the reduction half. And of course, I hope you still remember, you want to combine half and half, what must be the same before you combine half and half? Để cho mình字吧。So I need to call names. That means you have oxidation half equation, reduction half equation, and then you combine the two so that you get one overall equation, isn't it? So before you can combine the two, what must be the same? Let's say number of electrons, right? That means both half must be having same number of electrons, or else you multiply them first before you combine them. So for this one, tell me, after you multiply them, you combine them, what is the correct balancing? What is the correct coefficient? And what's the correct number in front? This one is before the balance, the number of electrons. So tell me what will be the number involved. So isn't it? Now of course, if you go for the half-half only, hold on, half-half letak bawah. So that means the half-half, number 1 is your what? Tin 2 becomes tin 4, isn't it? Sn2 become Sn4. So of course you know how many electrons involved, and of course another one is this one. Becomes this. So of course involving electrons, oxidation means you donate electron. So it means the electron must be here. This one is reduction process. Manganese 7 becomes manganese 2. Reduction. So reduction means your electron will be here. So of course you need to decide how many electrons involved, isn't it? Before you can balance the others. Is that right? Okay. So yesterday, from the back, let's go through, isn't it? Okay, Sophia. Tin 2, tin 4. Donate how many electrons?
Two. Two.
Okay, 2 electrons, isn't it? Okay. Okay. Manganese 7 becomes manganese 2. Accept how many electrons? 5. Okay. This one is 5. See that, isn't it? Because the rest all balanced already. 1 Mn, 1 Mn. 4O, so here 4O. 4 water means add hydrogen, so add hydrogen also. So there, isn't it? So before you combine, it means the one on top, of course, you need to multiply because the one on top 2 electrons, the one below 5 electrons. So see that, isn't it? The one on top need to multiply by 5, the one below need to multiply by 2. So as the result, the one on top multiply by 5, so you're getting 5 Sn and Sn2 and 5 Sn4, isn't it? Okay, the one below multiply by 2, so that means you get 2 MnO4. Multiply by 2, you get 16H. Right? The one below multiply by 2, you get 2 Mn2. Multiply by 2, you get add water. Right? So that will be the correct balance equation. Isn't it? So where tin 2 act as the reducing agent. Okay, now I hope writing all this equation shouldn't be a big problem to you. Chapter 8, you study all this half oxidation reduction. Okay, and then T2 also can, reduce nitro compounds. Okay, of course, this one don't worry, they will not ask you to write. Okay. So for example, so in this reaction, of course, you find that the nitro will be reduced to amine. Okay, and of course your tin 2 oxidized to tin 4. So all this involving showing that Sn more stable in positive 4 oxidation state. Okay, because it actually in a lot of chemical reaction it acts as a reducing agent. So it self oxidized. So that means tin Sn, stannum Sn, more stable in positive 4. Okay. Now for lead Pb, of course positive 2 is more stable than positive 4 oxidation state. So that's why lead 4 oxide normally would be a strong oxidizing agent. Okay. That means it will oxidize itself to lead 2. And lead 2 normally stable, no change to lead 2. Okay, for example, lead 4 oxide act as an oxidizing agent. So would oxidize concentrated HCl to chlorine. That means lead 4 would be reduced to lead 2. Isn't it? So there's our PbO2. So positive 4 here becomes positive 2 here. That. And of course your Cl here, negative 1. The Cl here, negative 1, becomes chlorine gas, 0 oxidation number. Isn't it? So the chloride is oxidized to chlorine. And of course your lead 4 reduced to lead 2. So of course in this case the lead 4 oxide is the oxidizing agent. And of course the concentrated HCl, that one will be the reducing agent. Okay, and then of course we find that lead 4 oxide, of course, when heated with aqueous manganese 2 sulfate, okay, in the presence of excess nitric acid, then you find that manganese 2 will be oxidized to manganate 7. Terbalik from just now. Then manganese 2 becomes manganate 7. And of course, lead 4 here becomes lead 2. Now, of course, we don't know what salt is this because don't know what acid here. But here, this one make use of nitric acid. Of course, if nitric acid, that means you get a lead 2 nitrate, no? Isn't it? Of course, if you want to put in the full name of the acid, no problems. Okay? Or just make use of the ions so that you are able to view the oxidation and the reduction. Okay? That so that's some of the chemical reaction which of course shows which oxidation state is more stable for elements involving group 14. Okay, so stability of positive 2, positive 4, well, settle. And all these chemical reaction, make sure, like it or not, it can be asked anytime in the exam. So for this one, let's say when lead 4 oxide is heated with aqueous manganese 2 sulfate in the presence of excess nitric acid, then of course you find that manganese 2 actually oxidized to manganate 7. So if question asks you, what is the chemical, or should I say, what is the observation in this process? Then of course very obvious, you find that a colorless solution, your manganese 2 colorless solution of course becomes purple, isn't it? And then you find that your lead 4 oxide. What's the color of lead 4 oxide? This one from yesterday's session, What's the color of lead 4 oxide? Moving up from the back. Lim Chong-yi, what's the color of lead 4 oxide? Imagine if question need you to describe the observation. More than 1 marks. That means you need to give more than one answer. Yeah, brown, isn't it? And what's the color of, for this one, of course, your product is a PB only. So for this one, that means if question need you to write the observation. Of course, number 1, very obvious, your colorless solution becomes purple. Number 2, of course, the brown solid. Yeah, lead 4 oxide is brown in color, true? So you find it in this process, of course, your brown solid dissolve. Because reacted already, right? You see your product where got solid? Your product not solid or so that means your brown solid dissolve. Even though you get your salt of lead 2 nitrate. Lead 2 nitrate dissolve in water, so you can't see it. Okay, get that now? So that will be the 2 observations. Right. In fact, if you check this one, so now your PbCl2, of course, this is a white contain water here. Contain water, of course, then you should name this one as a white precipitate. Get that? So for this reaction, of course, if question need you to tell what is the observation. So number 1, of course, your brown solid dissolve and a white precipitate is formed. And then of course you get a greenish yellow gas with pungent smell is produced. See that? So sometimes, of course, if you know the equation, it's quite easy to predict what is the observation. But you need to prepare yourself with observation for this one, even though we don't really conduct this type of experiment, and then no specific notes about this reaction, but still based on the equation and based on your knowledge of their separate color, so more or less you should be able to assume what you can see. Where's observation? So don't be surprised question asking about observations for all this chemical reaction, which of course only act as an example, in your content here. But still, of course, it can be asked. Don't say, I didn't do this one. I don't conduct this experiment. Of course, you don't conduct, but knowledge you need to know. Huh? Okay, so there. So some of these example prove to you which oxidation state is more stable. Okay, some of them of course positive 4. In fact, most of them positive 4 lah. Only lead will be positive 2. And of course, there are some chemical reaction which shows that lead definitely prefer, or should we say more stable in positive 2. That means spontaneously, the positive 4 would react and change itself to positive 2. Okay? So that will be the case. And of course, a little bit on some other side information. Make sure you know what does it mean by coordination number. Okay, it is a number of donor atoms or ligands which surround a central metal atoms in a complex ions. So that means the so-called coordination number, you may understand like how many bonds. And of course, this one is mainly for complex. That means in a complex, you look at the metal and then see that metal actually form how many bonds with, well, other groups. Other groups can be from other atom or it can be ligand. Ligands normally like a molecule. When complex, for example, still recall the complex ions. Of course, this one you encounter more later on in the last chapter for semester 2 lah. So of course you should know what is ligands and so on. But just let you know beforehand what does it mean by coordination number. Okay, coordination number referring to the number of ligands or number of atoms which surround a central metal atom. Of course, talking about a complex. Okay, there. Ligand, of course, can be atom, can be a molecule, can be an ion. Generally, we call them ligand. And ligand, normally, the character is it has at least one lone pair of electrons. Okay, so ligand normally donate the lone pair electrons to the empty orbitals of the central atom. So central atom, of course, in this case, can be from group 14. Okay, or of course, normally that central atom definitely is transition because transition have plenty of empty orbitals. Because transition normally would be a period 4 onward. So they have, 3D, they have 4D, 4F, plenty of orbitals. So they can receive the lone pair from ligand. Okay. So that type of bond definitely is a dative bond or a coordinate bond, we call it. So group 14, silicon, germanium, tin, lead, they all can form complex ions with a maximum coordination number of 6. That means they can surrounded by 6 ligands. Okay, there's you imagine, let's say, if they combine with 6 water, that's how we get the hexa aqua, because water is aqua. Okay, so that is called coordination number. In other words, the number of dative bonds. Okay, so that means 14 actually like transition, maximum they can go until 6. Because even transition also maximum is 6 only. Okay. Now, these elements, of course, use the empty d orbitals in their valence shell to receive lone pair electrons donated by ligands. Okay, and of course, if you check how the formation of complex, so all group 14 elements can form complex ions just as transition. Okay, using the empty d orbitals. Of course, except carbon, because carbon period 2, no d orbital. Okay, then for example, hexafluorosilicate. This one, yeah. There. So that means silicon can forming 6 dative bond with fluorine, or in this case is the fluoride ion. Okay. So that's similar. Of course, all this we're talking about F or Cl lah. Of course, no Br, no I, because the size is too big, not stable. Okay. So that the ligands, or should we say the complex ion formed by group 14 elements. You can do that. So of course the central atoms, I mean in this case would be the silicon, the germanium, the tin, the lead. So of course they make use of the MTD orbitals to expand their valency from 4 to 6. Because by right they are positive 4, okay, but now it can to 6, maximum 6, okay. So that means they're all able to show coordination number of 6. Group 14, Now, of course, carbon cannot form complex ion, okay, because there are no MTD orbitals in its valence shell. So the coordination number of carbon never more than 4. I mean maximum 4. But the rest, of course, is either 4 or 6. But always remember, normally no 5. 5 is for group 14, group 15. Okay, group 14 will be 4 or maximum 6. Okay, and then of course another term, make sure you know what is that. Okay, catenation. What is the meaning of this term? Just as you study what is proportionation, you must know. So all these terms, may pop up. So catenation refers to the ability of an element to form bonds between atoms of the same element in chain form. These are, of course, the most popular we know is carbon, isn't it? Okay, I mean when you study alkene, the carbon can be as long as you like. So C can connect to C, can connect to C, can connect to C. So catenation. Okay, and of course all these connection would be covalent bonds. So of course metal, even though yes we know metal, all metal will be giant structure. For example, sodium. Of course sodium connect to sodium, connect to sodium, connect to sodium, connect to sodium, long. But it's not in chain form. That one is in giant structure, and the bond is metallic bond, isn't it? So this one catenation normally refers to all those covalent bonds, and they can form a chain form. So the most popular, of course, carbon. Group 14, okay? So carbon undergoes catenation to form rings, to form chains. Okay, it can be single bond, can be double bond, can be triple bond. Covalent, so that means carbon can catenate. Okay, that means carbon has a catenation properties. Carbon can. It can be in ring form, isn't it? Now, silicon does not form many catenated compounds because silicon bond is weaker than carbon bond. That means silicon also can, but not as long as carbon.
No.
Okay, and silicon normally can silicon, but not just Si alone. Okay, but also can, but of course a bit less compared to carbon. Catenation. Germanium, tin, and lead, sorry, they does not form catenated compounds. Cannot, okay? That means you don't have Sn connect to Sn connect to Sn through covalent bond. No, okay? Because Sn doesn't have a catenation character, okay? So that is what it means by catenation. Okay, so there with that, we settle for this part. And that means talking about the stability of positive 2, positive 4. Make sure you know how to give reasoning. Actually, the reasoning is quite simple. And of course, plus you know what is the meanings of coordination number and what do you mean by catenation. Okay, catenation. So then that settle for 11.3. So for chapter 11, we still have Thursday. Won't be able to finish everything. We still have point 4. It's talking about Si. 11.4 is talking about silicate. That means the compound of Si, mainly Si, because Si, you need to know like it present in glass, present in sand, present in a lot of minerals. Si, so we focus on that. 11.4. 11.5 are tin. Yeah, that one less than 5 minutes so let's see, isn't it? Well, let's say I try to finish everything on Thursday. So next week it goes into group 17. Almost done. Okay, so this one is 11.3 stability. So just remember, going down group, positive for oxidation state, stability for positive 4 decreases, but stability for positive 2 increase. Okay, I mean the reason, because going down group, you find that size getting bigger, covalent bond getting weaker, so the energy released during the promotion of electrons from s orbital to p orbital, well, less energy will be released, so that energy cannot compensate, okay, for the energy needed for the promotion of the electron take place. So as a result, you find that positive 4 getting less stable. Okay, positive 2 become more stable, especially in lead. Because for lead, the 6s and 6p orbital has a great energy difference between them. So for 6s electron to promote to 6p, it's not taking place because too much energy needed. So that means lead actually would be having prefer that inert pair effect and maintain stable at a positive 2. That means just the P2 involved in chemical reaction, okay? Not going to promote electron from the 6s to 6p. Okay, one is the energy involved is too much because the energy level between the two is a big level, a big gap between the two. Number 2, because actually it become more stable due to the inert pair effect. Okay, so then we settle for this part. So before we part, so now let's see. 现在全部有几个人呢？ how come not many is here? Where is the others? Let me see. Hmm, 全部在了吗？ 1, 2, 3, 4, 5, 15, 16, 17, 18, 19. Okay, let me take a final shot here. Okay, so later on I will send exercise into group. For those who still owe me exercise, bayar hutang cepat-cepat. Okay, so I guess, well, that's all for today. Thank you for joining. So see you on Thursday.
老师，
啊？
第9跟第10课的那个练习答案有吗？就是这个。
你要一次 remind 我啊，我每次都忘记，然后又在那边挖，有时候挖还没有挖到，就等一下我又忘了。
OK
I try my best.
然后老师你这样每次因为你是这几天你是早上发 PPT 嘛，那个练习你是因为你还没有那个去弄好它。